Presentation and the simple example first. And then we recognize that as long as the middle block in cascade is identical, it doesn't matter what I put in here, right? It's still PR. In particular, if I choose this block to be a 2-point DFT, you can see this as 2-point DFT, okay? There's 1, 1, 1 minus 1. It's a 2-point FFT, right? Like this. And moving this to the other side, I can show that the corresponding filter will also be a higher wavelet. Okay? So that could be at the end of the lecture. Basically, we learned about factorization, right? We learned about polyphase representation for efficient implementation. We also use polyphase to show that it is easy to construct, right? So there are many ways to choose these choices. We change this block and keep them to invert each other. You have all the choices here. They might not be useful. Next time we will continue. We will get more blocking here and have longer system, right? As long as you cascade, you can take the inverse. You're done. So structurally, you're enforcing the PR condition by choosing the polyphase representation of the analysis and synthesis to be the inverse of each other. As long as they inverse each other, you're always going to be PR. So that's another way to represent VFPR system by choosing a block in the middle to be inverse of each other. And here's one example. Okay? So that's the end to it. What's next? Ở khoa trường 11 giờ hỏi câu hỏi đi ha. Question. System analogy. So what are the applications of wavelet filter bank, right? So my plan for the course is on Monday when we continue, I will use the projector. I will show you what I will talk about wavelet. So far we have not discussed wavelet, right? So you have no idea what wavelet means, okay? I'll show image and what are the wavelet representations of the image and why is it important. And then we'll discuss what are applications. So you can talk about adaptive filters, you can talk about noise reduction and so on and so forth. Okay? So Monday we'll show some images and show the resulting of applying wavelet transform for images and how is it useful and important. Okay? And then we'll look at the trade-off between different systems. So you apply a higher wavelet and look at the result. And we're applying a 97, which is the one that JPEG 2000 used, and see the result. And see what, why do we use one over the other. Okay? And then on Tuesday, I'll show you an image compression toolbox. So a friend of mine at Wisconsin, he designed a very nice toolbox for PC, and it's be available in the lab also. And there you can actually pick an image and then apply JPEG, look at compression, and then use the same bit rate, okay? And apply wavelet and see what are the trade-offs. And you will see that JPEG have blocking artifact, right? And wavelet have ringing artifact. And we'll discuss, what are the trade-offs between different set of wavelets and so forth. So the next 2 days, you'll see how this applies. Just bear with me until then. I know this is, hard to see what is useful, but this is setting the fundamental for the theory. Okay? And the trade-off more generally depends on application, right? When they design JPEG, they say, okay, can I use block 8 by 8, or can I use 16 by 16, or 12 by 12, and so on and so forth. So there's a whole study of designing different transform, DCT transform, for all of this. And it turns out that this block is good, because back in the 1980s when they designed JPEG, the highest resolution we have is SIP, right? This is 352 by 288. That's the size of the image. And that size of the image, 8 by 8 system blocks work pretty well. Have the most correlation for compression. Okay? But this is too expensive, because back then in the 1980s, a megabyte of RAM is very, very expensive. Okay? A computer have 32 meg or 64 meg. Right? That's a PS2 computer. Okay? So it's very expensive to use a big block, because a big block requires more memories in the cache, right? Because the speed of computation is not only in how many multipliers, but how big the block is. Right? If you load in a block, if the block is too big, you miss the size of your cache. If you go outside the cache and then bring it in, that operation is much slower compared to the speed, right? Okay, so the way that you're choosing the block size depends only on the cache size. So they say that for this size with a 32 kilobyte cache back there, 8 by 8 works pretty well. So we use 8 by 8.